Hey everybody, it's Eric. Today I'm going to show you something very cool that I found and how to represent it on Geometer's Sketchpad. First off, let's take a look at this video. Have you ever ridden a double Ferris wheel? If you have, did you ever think of what kind of curve you are traveling in while sitting in the seat? This lesson will take a look at this curve. This curve is actually called a cardioid. The word cardioid comes from the Greek root cardi, meaning heart. It can also be defined as the curve traced by a point of a circle that rolls around the circumference of a fixed circle of equal radius without slipping. Here's a demonstration. The blue circle shown is the fixed circle. The green will be the circle that rolls around the circumference of the fixed circle. As you can see, the red line that is being traced out is our curve, which is the cardioid. So here's a little history and description of the cardioid. The cardioid was developed by the Danish astronomer Ole Christensen Romer in 1674. It was discovered during an investigation to find the best design for deer teeth. The name cardioid was not given to the actual curve until 1741. The resulting curve is roughly heart-shaped with a cusp at the place where the point touches the fixed wheel. As you can see to the right in polar equations, these are the four main equations and layouts for the curve of the cardioid. Here, in polar coordinates, we will look at the four basic equations for the cardioid, which are listed on the top left side of the page. First, I will show 2 times 1 minus cosine of theta. As you can see, the cusp is on the right. Now, if I graph the next one, all we are changing is the minus sign to a plus sign. So we have 2 times 1 plus cosine of theta, which, as we can see, if I hide the first one, the cusp is on the left. So as we can see by these two, cosines go left and right on the grid. For our next cardioid, I will graph 2 times 1 minus sine of theta. As you can see, the cusp is on the top of the cardioid. If I graph the next one, we are changing the sign, and we have 2 times 1 plus sine of theta. And if I hide the first one again, we can see that it's just flipped around and the cusp is on the bottom. So here we have the four main equations for the cardioid. The sines going up and down, and the cosines going left to right. Here we are with the basic equation of a cardioid. 2 times 1 minus cosine of theta. Now, if we wanted to make this curve larger, here's what we do. Instead of multiplying by 2 in the equation, multiply by a larger number. Here I have 3. As we can see, the blue curve is much larger than the red. Now the same goes if you would like a smaller curve. Just multiply by a smaller number. Here I multiply by 1/2, and as we can see, the small blue curve inside the red is quite a bit smaller. Alright, so if I hide these two equations, I will show you 2 things that you cannot do to manipulate the equation of a cardioid. First of all, here I changed the 1 to a 2 inside the parentheses of the equation. So I have 2 times 2 minus cosine of theta. As you can see, on the right side of the blue curve, there is no cusp, which makes this not a cardioid. For the next one, I've added 3 to the end. This is another thing you cannot do. As you can see again, on the blue curve there is no cusp, which results in not a cardioid. Here I will graph and animate a cardioid in parametric equations. I am using a slider with a length of 2 pi and it is labeled AB. Our equations, as shown here, are 2 times the cosine of measure of AB times 1 plus cosine of measure of AB. And the other one is 2 times the sine of measure of AB times 1 plus cosine of measure in AB. And when we graph and animate this equation, our cardioid appears. Pretty cool, isn't it? And here we are back at the double Ferris wheel. Can you visually see a chair making the curve of a cardioid yet? Well, here we go. Hold on tight. As you can see, the blue chair is outlining the curve of the cardioid. And there we have it. So next time you see a double Ferris wheel, watch a chair and outline the curve of a cardioid. And of course, think of me, the man who made your cardioid inspiration come true. So see you next time.